In lab, you guys have been looking at waves, and it's worth noting that we've been looking at waves that are only moving in one dimension along a string. And the rules we're finding here, we're going to apply to some other places, to some other waves, but we are starting there. So what we started with was a string vibrating with one loop. So we took a string and stretched it between 2 points, and we knew the length or the distance between those 2 points. We're going to call that L for the length of the string. And then you made that thing resonate or vibrate, create a standing wave of one loop. And from that, we know the wavelength of that wave is actually equal to twice the length of the string, because that's only half of a wave right there. Remember, this is a node, and we have an antinode in the middle. Then, and you found the frequency at this. Now this is actually called the fundamental frequency, because this is the first vibration that will fit and resonate and create a standing wave right there. So F1 and lambda 1 are the fundamental ones. They're the ones that we start with. And so this is our fundamental frequency, our fundamental wavelength. Then you change the frequency until you got a second wave to fit on this string, or a second loop, I guess. And so now we have a complete wave. And so we went to lambda 2, which is equal to L. The wavelength of this wave is the whole length of the string, and then we have F2. And what we found was F2 is actually about twice F1. And this pattern continues. So then you went and you got another node, and so we had a wave and a half. We had 1, 2 nodes in the middle, 3, 4 nodes if we count the ends, and we had 1.5 waves. So now we're getting the pattern where lambda 3 is 2/3 of L. And so what we want to do is we want to find a relationship where we know, hey, these are overtones or harmonics. What's the wavelength of the nth harmonic, and what's the frequency of the nth harmonic? And if we found this one, we found that F3 is also equal to 3 times F1. And so we can come up with formulas for these where basically, if you look, this is 2 over 1, this is 2 over 2, this is 2 over 3, and this pattern fits. So the wavelength of the nth harmonic is given by 2 over n times the length of the string that it's vibrating on. And the frequency of the nth harmonic is given by the fundamental frequency times n, whichever frequency we're looking for, whichever overtone we're looking for. Now there is another relationship going on here. Remember, V is equal to wavelength times frequency. So if we combine these two things, we should be able to come up with the speed of the wave for the wave moving on the string. And so if we take wavelength of the nth harmonic, which is 2 over n times L, times the frequency of the nth harmonic, which is the fundamental frequency times n, that n cancels that n, and we get V is equal to twice the length times the frequency, the fundamental frequency. So you can calculate the speed of a wave based on the length of the string and the frequency of the fundamental. Now, there are some other things that are going on in here. This is the speed of the wave if I know the wavelength and the fundamental frequency, but what actually determines the speed of a wave? Well, remember, the speed of a wave is determined only by the medium. Depends on the medium, that is what it's moving through. So this wave is a vibration that's carrying energy from one place to another. And what you guys noticed is if you increase the tension in the string, if this goes up, then so does speed. And if we think about why, okay, the string is made out of a bunch of little pieces that you can think of them as being stuck together, whether they're atoms or strings or sections or whatever you want to think about. These things are stuck together, and there's a connective force. There's a force between them that binds them together. And so when we take and apply a little bit of force this way to this particle, it's going to then exert a force on this particle, and a force on this particle, and a force on this particle. And then when we pull it back down, this gets pulled back down, pulled back down. And so you get a wave motion that travels from one segment to the next segment to the next segment because they are connected. And the force that connects them is tension. That's how much force is there. So if these are connected, if there's more tension between them, there's a stronger force between them, then this motion is able to travel more rapidly through the string segment. And so increasing the tension speeds up the wave because it speeds up how quickly one particle affects the next particle. But the other thing that's there is we noticed if we used a heavier string, then the speed decreased. And if you think about that, that's because mass is a measure of inertia. The more inertia something has, the harder it is to make it accelerate. And since these are constantly accelerating, a heavier string is going to take a little bit more force to make it accelerate at the same rate, or it's going to accelerate slower. And so what we have is this relationship between force and mass, just like we had in Newton's laws, that describes the motion of the string. But there's a nice equation that we can derive that actually tells us the speed, how fast a wave will move along the string. And it depends on the linear density, and linear density is exactly what it sounds like. If density is mass divided by volume, then linear density is not mass divided by volume, because that's volume, it's mass divided by length for the line. So this is mass over the length of the string, and that tells us linear density, and that would be measured in kilograms per meter, not kilograms per meter cubed. Okay, this thing has the symbol mu, so we have the linear density of the string, mu, and we have the tension force, and we can actually put those together to find the speed of a wave moving along a string. And this is given by V equals the square root of the tension, Ft, divided by the linear density of the string. Now, just from a units perspective, let's make sure that works. Force is newtons, and linear density is kilogram per meter, or if we're dividing, then meters per kilogram. And if we take a look at that, then a newton is a meter per second squared times a kilogram, and then I have that times meters over kilograms. So the kilograms are gone. Meter times meter equals meter squared. Seconds squared are still there. We square root all that because it's under the radical, and we do see that this does have units of meters per second. So it does work dimensionally, and it should work in practice. You guys should be testing that in lab. So hopefully that works out for you. Okay? So we have a couple equations. We know that f of the nth harmonic is given by f1 times n. That's our fundamental. We know the wavelength of the nth harmonic is given by 2L over n. Again, this is the nth harmonic. We know that the frequency times the wavelength is equal to the velocity, and we know that the velocity of a wave moving along a string is given by the force, the tension in the string, divided by the linear density.